Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over infinite limits. What exactly happens when we can't get that factor that makes our denominator 0 to cancel out? So what are infinite limits? Well, an infinite limit occurs when x approaches some value a as our function f of x approaches some arbitrarily large, either positive or negative number. So if we're looking at this picture on the left, you can see that as x approaches 5, our function approaches some arbitrarily large positive number, and we will call that infinity. So the limit as x approaches 5 of our function f of x is equivalent to infinity. And infinity, that symbol is drawn like a sideways 8. Now, if you're looking at this picture over here, as x approaches 2, our function from both the left and the right is approaching what? Well, it's approaching negative infinity, some arbitrarily large negative number. So this will be written as the limit of f of x as x approaches 2 equals negative infinity. So an infinite limit is defined as the limit of f of x as x approaches a, and that's going to be equivalent to either a positive or a negative infinity. As x approaches a, if f of x approaches an arbitrarily large positive number, then we're approaching positive infinity. As x approaches a, if f of x approaches an arbitrarily large in magnitude negative number, then we say it approaches negative infinity. Now, if we get a positive infinity or negative infinity, technically speaking, that limit still does not exist, except we have a way to write that limit so it helps us visualize what's happening to our function. So even though these limits technically do not exist as we approach positive infinity or negative infinity, we get an idea of how the function is behaving. Now, continuing along the lines of limits not existing, from the left and from the right, for each of these, we approached the same sort of values. So we went towards a positive, arbitrarily large number, or both right and left sides went towards an arbitrarily large negative number. But let's look at this next picture. Look at the limit as x approaches 5. Well, in this case, as we approach 5 from the right, we're going towards positive infinity, and as we approach from the left, we're going towards negative infinity. So the limit in this case, the limit of some function f of x as x approaches 5, we would say does not exist. So up above, how we said, okay, it was heading towards infinity, or our function was heading towards negative infinity. Here, because the right and the left do not go towards the same values, we say does not exist. However, if I break this down, the limit of f of x as x approaches 5 from the left equals negative infinity, and the limit of f of x as x approaches 5 from the right equals a positive infinity. This information here is more helpful to us than just saying does not exist for the limit, because then we can really visualize the shape of our graph. In each of the above graphs, we have a vertical asymptote. But what exactly is a vertical asymptote? Well, it's a line that our function approaches as we approach that finite value in the x. So as you can see in our first graph, as x approaches 5, our function approaches positive infinity, but there's also some vertical line that our function is getting closer and closer to, and that's the line x equals 5. In the case of this first graph, that's our vertical asymptote. Our function goes towards infinity, getting closer and closer to that line x equals 5. Whereas in this second graph, our vertical asymptote occurs at that a value, again, x equals 2. As our function goes towards negative infinity, it's also getting closer and closer to the vertical line x equals 2. And then, looking at this third graph, even though that right side limit went towards positive infinity and that left side limit went towards negative infinity, both are still approaching the line x equals that a value of 5. So vertical asymptote occurs when the limit of f of x as x approaches a, either from the right, left, or when those are equivalent, equals positive or negative infinity. So vertical asymptote occurs when the limit of f of x as x approaches a equals a positive or negative infinity, and also when the limit of f of x as x approaches a from the right equals a positive, negative infinity, or when the limit of f of x as x approaches a from the left equals positive or negative infinity. As we saw in the case of that last graph, the limit from the right and the left do not have to head towards that same infinity. They just have to head towards some arbitrarily large number. And if that's the case, then our vertical asymptote is the line x equals a. If either of these is true, then we have a vertical asymptote, and that vertical asymptote is the line x equals a. Now let's go over actually calculating these infinite limits. But think about how we even got on this topic of infinite limits. That occurred when we were taking the limit of a rational function where that denominator was undefined and couldn't be canceled out. So how are we going to solve for these limits if we still can't cancel out the denominator? Well, let's take note that a constant divided by a very small number approaching 0 is either going to go towards infinity or negative infinity. Think about it. If I have 1 over 100, that's a fairly small number. But then if I divided 100 by 10, then I'm going to have 1 over 10. That's a small number, but a slightly less smaller number. If I divided it again by 10, then that'd be 1 over 1. Well, now we're at a whole number, we're no longer at a fraction. Or let's think about if I divided 1 by 10. Now I would have 1 over 1/10, which equals 10. Or if I continued on with this pattern, 1 over 100, that's going to be equal to 100, and so on. As my denominator gets smaller and smaller, my overall number gets larger and larger. So if you can envision 1 all over 1 over a million, that fraction, 1 over a million, in my denominator is really small, but my overall fraction, 1 over a million, is equal to a million, an extremely large value. And if I make my fraction even closer to 0, moving on from a million, let's go to 1 over a billion, then my number is even larger. So you can see that as we get closer to 0, the overall fraction gets larger. However, think about this. What if our numerator was negative? Well, then our overall fraction would go towards a large negative number, because a negative over a positive is a negative. What if they were both negative? Well, then our fraction would go towards a large positive number. Or what if just our denominator was negative? Positive or negative, it would go towards a large negative number. So the signs of both the numerator and denominator come into play and are important for figuring out which way that function's heading, whether it's going towards positive infinity or whether it's going towards negative infinity as x approaches some value a. So let's take a look at this in example 1. In example 1, we're going to evaluate the following limits. And our first limit is going to be 7 over x as x approaches 0 from the right. Now, if we plugged 0 right on in for x, you would see that our denominator is indeed undefined. And there's no way to cancel it out or factor it out. If we had an x up here, sure, we'd be able to cancel it out. That limit would be equivalent to 7. However, we don't, so we're going to need to use the concept above to help us solve for this limit. Now think about approaching 0 from the right. If we're approaching 0 from the right, What is the sign of our denominator? Well, the sign of our denominator is always going to be positive. So our denominator is approaching 0 and it's positive. And what's our numerator doing? Well, our numerator is always that constant. So I'm just going to write that it's a constant of 7 in this case. So because we have a constant over a number that's getting really, really, really small, our overall fraction is going to get really large. So when we have some constant or approaching some constant over our denominator that's getting really small, the overall fraction gets really large. So we're approaching 0 from the positive side, and there's a positive 7. Let me make a note that that's a positive 7. So we're going to have a positive over a positive. So this limit is going to go towards a positive infinity. Whereas in part B, we have the same exact fraction, except now we're approaching from the left of 0. So our numerator still is a constant of positive 7. But our denominator now, well, it's still approaching 0, but it's approaching 0, and those numbers to the left are 0 are negative. So because we have a positive over a negative, our overall result is going to be negative, but as we approach some constant over a number getting smaller and smaller and smaller, the overall fraction gets bigger and bigger and bigger. Positive over negative is a negative, and this goes towards negative infinity. So you can see whether we're approaching from the right or whether we're approaching from the left will come into play when calculating the limits of our function. So you can see that if I made it negative, that would switch both of the signs for my infinities, because then I'd have a negative over a positive for A and a negative over a negative, which would be a positive for B. So again, the signs are very important when figuring out what our function is approaching. So now that we understand this concept a little more, let's move on to example 2. In example 2, we're going to be evaluating 6 different limits. And we're going to be evaluating those limits for our function f of x that's equivalent to x over x minus 2 times x plus 3 squared. So right away, looking at our denominator, which 2 values of x can we not have? What makes our denominator 0? Well, that's going to be when x equals 2, our denominator is going to be 0, and when x equals a negative 3, our denominator is going to be 0, because each of those factors, if either of them is 0, our entire denominator is 0. And as you can see from our numerator, we cannot cancel out either of those factors. Because we can't cancel those factors out, when x equals 2 and when x equals negative 3, what are we going to have? We're going to have a vertical asymptote at x equals 2 and at x equals negative 3. We're up above. As x approached 0, our function approached a positive infinity from the right and a negative infinity from the left. So even though the limit as x approached 0 of our function 7 over x does not exist, because they're not approaching the same value from the right and left, we still have that vertical asymptote at x equals 0. So again, in example 2, we can't cancel out either of those factors from our denominator. We know we have vertical asymptotes at each of those values. But let's talk about the limit of f of x as x approaches 2 from the right. Let's think about what is happening to our numerator and our denominator. In our numerator, what are we approaching? Well, we're approaching 2. As we approach 2 from the right, we're approaching some constant of 2, and that's a positive 2 that we're approaching. So our numerator approaches a positive 2. What's our denominator doing? Well, we know that this is approaching 0, because as we get closer and closer to 2, 2 minus 2 is going to equal 0. So as we get closer to that, we're approaching 0, And because we're coming from numbers greater than 2, like 3, 4, 5, we're approaching 0 from positive numbers. So right now, I know that I'm approaching 0. I just need to check whether I'm approaching 0 from positives or negatives, which, as we already stated here, we're approaching from positive numbers, but that entire sign of my denominator matters. So I also need to see what my sign of x plus 3 squared is. And regardless of what we're heading towards, because this is squared, we're always approaching from positive values. A positive times a positive in my denominator is going to result in a positive. So we're approaching 0 and we're positive. So approaching a positive constant over positive numbers, getting closer and closer to 0, our overall fraction is going to get larger and larger, and it's positive, because a positive divided by a positive is still a positive. So this limit, the limit as x approaches 2 from the right of our function f of x, is going to equal a positive infinity. Let's check out b. For b, we're now going to approach from the left side. And just like up above, our numerator is behaving the same way. Even though we're approaching 2 now from the left-hand side, we're still approaching that positive 2. So our numerator is approaching positive 2. But what's happening to our denominator now? Well, we already talked about how when we square this, regardless of whether we're approaching from the left or the right, when we're squaring this number, that's always going to be a positive. But now, if we're approaching 2 from the left, we see that this factor is indeed approaching 0, so our overall denominator is approaching 0. And it's approaching 0 from, well, think about plugging in numbers to the left of 2. 1, 0, -1, that would result in negative numbers, and a negative times a positive is a negative. So this is approaching 0, and it's negative. Positive over a negative is going to be a negative, and a constant over a number getting smaller and smaller and smaller is going to result in a very large number, a number that's getting larger and larger and larger. So this is heading towards negative infinity. My limit of f of x as x approaches 2, well, if coming from the right approaches infinity and coming from the left approaches negative infinity, well then my overall limit does not exist because I'm not heading towards those same values. Even though technically heading towards positive infinity and negative infinity do not exist, because we're not heading roughly towards that same arbitrarily large value, we say that this does not exist. Now moving on to d, we're going to be focusing on, for d, e, and f, that other factor in our denominator that makes our function undefined. And that's when x is equal to -3, this factor here is going to equal 0. So we know we can't just plug -3 right on in, so we're going to look at it like we did a through c. So for d, as we approach -3, our numerator is approaching -3. It's just approaching that constant. So this is going to be approaching a -3. So the sign in our numerator is negative. Now, as we approach -3 in our denominator, what all is happening? Well, as we approach -3, we know this factor is approaching 0. So our overall denominator is approaching 0. We just have to figure out whether it's approaching 0 from positives or whether it's approaching 0 from negatives. We know we're heading towards a negative infinity or a positive infinity. We just got to figure out which one. If I was to plug numbers from the right of -3 into this factor, sometimes I'm going to get negative numbers, and sometimes I'm going to obviously get positive numbers, because think about numbers to the right of -3. If I was to plug in 0, that's to the right of -3, I would still get a negative. However, if I was to plug, let's say 5 in, 5 is technically to the right of -3, but I get a positive now. But that's okay if I do get positive values. we need to look as we approach -3. So I only want to look at values to the right of -3 that are very close to that value of -3. So 5 is pretty far off there from -3 and is not going to help me as I'm approaching -3. However, plugging in, let's say, a -2.5, because that's to the right of -3 and fairly close to -3, that's still going to give me a negative. So this factor is going to be negative as we get closer and closer to -3. And this factor, well, think about it. As we approach -3, we're approaching 0 here, but we're always squaring it. So this is always going to be approaching 0 from positive numbers. So if we have a negative times a positive in our denominator, that's going to be approaching 0, and it's negative. So we have a negative constant over a denominator that's approaching 0 and is also negative. That fraction is going to get extremely large, and it's going to be positive because a negative over a negative is a positive. So this limit is going to be equal to positive infinity. So we know our numerator in this next part E is approaching -3. Our limit is different because now we're approaching -3 from the left. So let's take a look at our denominator. Well, as we get closer to -3, numbers from the left, this is always going to be negative. So this factor is negative, and we already know that our overall denominator is approaching 0, so I'll fill that in as well. And again, it's approaching 0 because this factor is getting closer to 0 as we get closer to -3. And again, we're squaring those values. So regardless of what x values we plug in, as we get closer to -3, this is always going to be positive. And a negative times a positive is a negative. So this is approaching 0, and it's negative. So approaching a constant over a denominator that's approaching a very, very, very small number, 0, is going to make the overall fraction get larger. And a negative over a negative is a positive, so this also approaches positive infinity. So when we discuss the limit of f of x as x approaches -3, because from both the right and left we approach to positive infinity, we're going to say that that also approaches a positive infinity. And what I've done, I've also graphed this so we can do a quick double check of our answers A through F. So here I've graphed our function. You can see that as we approach -3 from both the left and the right, we're going towards positive infinity, which we confirmed in parts D, E, and F. What I'm going to do now is I'm going to write that vertical asymptote so that you can see how we're approaching that line. So x equals a -3. Look how we're getting closer and closer to that line as our function approaches very large values. So as x approaches -3, our function approaches the line x equals -3 as it goes towards infinity. Now remember, for part C, as x approached 2, our limit did not exist because from the left-hand side we approached negative infinity, and for a right-sided limit we approached positive infinity. But you can see we still have that vertical asymptote at x equals a, or in that case x equals 2. So you can see that our function is getting closer to either infinity or negative infinity, while it is also approaching or hugging that line x equals 2. So let's go back to our worksheet and finish out a few more examples. So in this last part, I just want to touch base again with what makes a vertical asymptote versus a hole. Both occur when we have rational functions that are undefined, so when that denominator is equivalent to 0. A hole, however, occurs when we can cancel out that factor in our denominator that's making our function equal to 0. Whereas a vertical asymptote occurs when we cannot cancel it out. So for example 3, we're going to evaluate each of the following limits and also evaluate whether the function has a hole or a vertical asymptote at a. The limit as x approaches 1 of x over x plus 1. Well, if you're thinking, okay, this factor in the denominator can't cancel out, so I've got a vertical asymptote, you are correct, except this limit we can totally evaluate, because what makes this function undefined is when x equals -1, not when x equals 1. So in order to evaluate this limit, we just plug this right on in. So we're going to have 1 over 1 plus 1, which equals 1/2. So this limit is equivalent to 1/2. So I don't have a whole or a vertical asymptote when a is equivalent to 1. I just plug that on in, and I can evaluate my limit. So in this case, I have neither when x equals 1. Because remember, I wanted you to state whether it was a whole or an asymptote at x equals a, and in this case, it was neither at our a value of 1. But in part B, I now switch it up, and we're going to take the limit as x approaches -1. And we know that as x approaches -1, -1 plus 1 will equal 0, which will give us a function that's undefined, and there's no way to cancel out this denominator. So right away, I know that because we can't cancel that denominator out, and what makes it undefined is -1, I have a vertical asymptote, and that vertical asymptote is the line x equals -1. But let's go ahead and evaluate this limit. As we approach -1, our numerator approaches a negative constant, and as we approach -1, let's say from the right, think about values directly to the right of -1. That would be like -0.5, 0, 1. That's going to be positive. So as we approach -1 from the right, a negative over a positive, we're heading towards -infinity. But now let's think about it as we approach -1 from the left. As we approach -1 from the left, this still approaches -1, so it's still approaching a negative. But think about as we approach -1 from the left, obviously this denominator is approaching 0, but it's approaching 0 from negative numbers. Think about plugging in -1.5, -2, -3. That's approaching 0, but from negative numbers. So because the denominator is approaching 0, I know I'm going towards some infinity, and a negative over a negative gives me a positive. So this approaches positive infinity. So because from the left and from the right do not approach the same, either positive infinity or negative infinity, we say overall that this limit does not exist. Moving on to part C, we're looking at as x approaches 4. If I were to try to plug in 4, this factor is going towards 0. However, remember, the difference between a whole and a vertical asymptote is whether I can get that factor to cancel out or not. So I'm going to start by factoring my numerator to see if I can indeed cancel it out. So this is going to be the limit as x approaches 4 of what multiplies to give me positive 4 and adds to give me a -5. That's going to be -1 and -4. So this is going to be x minus 1 times x minus 4 all over x minus 4 times x plus 3. You can see that as x approaches 4, my factor in my denominator that's making my overall function equal 0 cancels out. My x minus 4 cancels out, so I know that this is actually a whole when x is 4. And because it's a whole, that limit still exists. It's not infinity, it's not at negative infinity. My limit exists. I'll just plug 4 right on into my limit now. So plugging 4 in, I'll get 4 minus 1 in my numerator over 4 plus 3 in my denominator. Because I got that factor that caused my overall function to equal 0, cancel out, I plug 4 right on in. 4 minus 1 gives me 3, and 4 plus 3 gives me 7. So this limit is equivalent to 3/7. And lastly, we're going to look at this next part D, which is the same exact fraction as up above, so I'm going to rewrite that in its factored form. you can see that as I plug in -3, well, the denominator is going towards 0. And I can't cancel that out, so I know I do indeed have a vertical asymptote at x equals -3. And that vertical asymptote, again, is equivalent to x equals -3. But since this function can simplify down, why don't I just work with that simplified version? Let's leave my x minus 4's canceled out. So I'm just going to work with the limit as x approaches -3 of x minus 1 over x plus 3, because that's a little bit easier to work with when we're talking about whether we're approaching positives or negatives as we approach 0. So looking at our numerator, if we were to plug in numbers closer and closer to -3, well, that overall numerator is approaching -4. Whereas our denominator is approaching 0, we just got to figure out whether it's positive or negative. And that's going to be based on whether we're coming from the right or from the left. If we're coming from values to the right of -3, like -2.5, -2, 0, you can see that that's going to be positive in our denominator. Whereas if we're coming from values to the left of -3, that would be like -4, -5, then this factor is going to be approaching 0 from the negatives. So even though we're approaching 0, coming from the right and coming from the left, we're approaching it from positives or negatives, which is going to make our sign of our infinity flip. So coming from the right, we're going to be approaching negative over positive. That's going to be a negative infinity. And coming from the left, negative over negative, we're going to be approaching positive infinity. So this limit does not exist. And just so you can visualize the difference between a whole and a vertical asymptote, let's go ahead and graph this real quick. So here we have it. I've graphed our function. We can see that we do indeed have that vertical asymptote at x equals -3, but when x equals +4, we don't have a vertical asymptote. Remember, that was a whole. So if I was to plug values into my function, you can see when I get to this point of 4, my function is undefined. You can see that whole in my function. And again, vertical asymptote, that factor in my denominator didn't cancel out, whereas for a whole, that factor in my denominator does cancel out. And again, because it is a whole, that limit still exists. My function was heading towards 3/7 from both the left and the right. So hopefully with this worksheet, you got a lot of practice with infinite limits. In the next video, we're going to go over no longer infinite limits, but limits at infinity. So as opposed to x approaching some finite value, we're now going to take the limit of some function as x approaches either infinity or negative infinity, now that you have a good understanding of what infinity represents. So stay tuned, and until the next video, good luck with your online learning.